Hello, everybody. My name is Rodney Lalonde. For those who didn't hear the presentation last class where we went around the room, I'm a fourth-year PhD student under Dr. Ulas Bagci, and today I'm going to be talking to you guys about this paper, which is called The Lottery Ticket Hypothesis, Finding Sparse Trainable Neural Networks, and it's by the authors Jonathan Frankel and Michael Carbin from MIT's Computer Science and Artificial Intelligence Lab. Just recently, this paper won Best Paper Award at ICLR for 2019. It was one of 2 papers to do so. And it really is a pretty groundbreaking work. I'm very excited to be able to present this to you guys. So hopefully I can make it a little bit entertaining. So there we go. Okay, so the lottery ticket hypothesis. I'm going to kind of give you guys some of the inspiration and some of the background behind how they came up with this, walk you through what their hypothesis is exactly, and then show you kind of the supporting evidence that they give via experimentation to support this hypothesis. So the background information / inspiration / motivation. In neural networks, it's a common conception that the deeper the better. If you look at large-scale tasks like ImageNet classification, models with more parameters or more floating point operations tend to achieve better results. This is seen very well if you look at DenseNet, for example, and you look at all of their experiments. They have some really nice curves in there that basically show exactly this, that the more floating point operations you have, the better results you get. And this is kind of a standard conception right now in deep learning. But then when you talk about the idea of sparsity in deep neural nets, you look at something like network pruning techniques where you can reduce the number of parameters by about 90% without hurting the accuracy whatsoever. And there's been a lot of papers that have different techniques to go about this procedure. Yanli Kuhn is one of the more famous ones, but there's a bunch of them here. They can decrease the model size, they can lower the energy consumption, and these 2 later effects are what make them extremely popular in embedded solutions, which is what's driving a lot of this research, is to be able to put these models on embedded devices. So this kind of brings up a question, right? If 90% of the parameters can be gotten rid of without hurting the results at all, do we really need them? What's the point of all these parameters then? And there's further evidence for this, that we shouldn't need deep neural nets. One of them is the universal approximation theorem. So I'm sure most people are familiar with this, universal approximation theorem. It was proven for a sigmoid single layer fully connected network by Cherbenko in 1989. And it was more recently proven for a 2-layer ReLU network in 2017. Basically what the universal approximation theorem is, because it looks like some of you might not know, it basically says that, in the first case, a single hidden layer fully connected neural network is capable of approximating any continuous function to within any given degree of accuracy, given an unlimited number of neurons within that layer on Euclidean space. So a continuous function in Euclidean space, you can approximate any function given a single layer neural network. And the degree of accuracy that you set determines the number of neurons you'll need within that layer. So if this is true, we can approximate any possible function. We should not need deep networks. We really only need single layer networks, or a 2-layer ReLU if you don't want to use a sigmoid. Mimic learning is another thing. So this paper came out in 2013. It's called Do Deep Networks Really Need to Be Deep? And they show that shallow networks can be trained by mimicking deep networks to achieve comparable accuracy to the deep networks. So again, this combined with the sparsity argument kind of suggests that we don't really need deep networks at all. But this also suggests something interesting. They were not able to train the shallow networks. And that kind of brings us into this, right? So not so fast. It turns out deeper is better during training. All the sparsification techniques take place at testing. The models are already trained. We throw away a bunch of parameters and it performs just as well. But during training, that's not the case. We're not able to train these shallow networks for some reason. And figuring out what the heck that reason is puzzled deep learning researchers for a long time now. So these pruned networks, when they're retrained from scratch, converge far slower and to worse accuracy than the deep networks that they were pruned from. So if you throw away 9% of the parameters and you take that network and you try to retrain just that network, it'll perform terribly. So the key that these authors found is in the initialization. So the discrepancy between training and testing, according to the lottery ticket hypothesis, the key is the random initialization at the beginning of the network, at the beginning of training. While in theory a shallow network should be able to perform just as well as a deep one, our current initialization and our optimization techniques fail to achieve this theoretical result. And so this is the big discrepancy that we're trying to solve, and the lottery ticket hypothesis claims to have solved it. Some further evidence from other papers. So this is a 2016 paper, training a pruned network from scratch performs worse than retraining a pruned model. During retraining, it is better to retain the weights from the initial training phase than it is to reinitialize the pruned layers. So this is a big piece of evidence for the fact that it's the initialization of the weights rather than the unique architecture that's found during the pruning process. And we'll get into that. So that's enough background. Let's get into what the theory says. As I claim here, I think this is a groundbreaking theory. So hopefully you guys are all super excited. This is what the theory says. It says a randomly initialized dense neural network contains a subnetwork that is initialized such that when trained in isolation, it can match the test accuracy of the original network after training for at most the same number of iterations. So I'm going to kind of walk through. So in other words, put more simply, creating very large, very deep, very wide neural networks can be thought of as composing together many different subnetworks. And if you guys are familiar with Dropout, this is actually the same principle that Dropout works on. In Dropout, we're randomly sampling subnetworks from the network and training each of those at each iteration that we drop. So, okay. Anyways. So the key is the bigger the network, the more randomly initialized subnetworks we have. And the authors say that each of these subnetworks can be thought of as a different lottery ticket. The more that we buy, the better chance we have of winning. So the bigger, the deeper, the wider the network, the more subnetworks it contains, and the better chance one of those subnetworks happens to get a random initialization that's good. That's the key. Hopefully it makes sense to everyone. I'm getting a lot of blank stares. So in other words, what defines a winning ticket is it's a network, pruned network, that can match the test accuracy of the original deep, wide network after training for at most the same number of iterations. Cool. So how do we test this hypothesis? So if this hypothesis is true, we should expect two things. One, that the lucky initialization is the key, not the architecture. So if we randomly reinitialize this prune network, we should expect it to perform worse on average, right? Because that pruned network with far fewer parameters is essentially like buying one lottery ticket. You may get really lucky and win the lottery buying one ticket, but on average, it should lose far more often than our special chosen weights that we pulled out from the pruning process that they proposed. So that's the big one. It's the architecture. It's not the architecture, it's the initialization. The other one is that the pruned network should perform at least as good as the deep network on test accuracy when trained in isolation. So if the initialization is copied over from the deep network. So basically what this is arguing is there is no benefit to a deep wide network other than you're buying more tickets, right? So if I found a winning ticket and I go take that winning ticket in, it should win, right? It should meet this test accuracy within this training. There shouldn't be any benefit to having this deep wide structure other than it allowed me to happen to get one of these winning combinations of initialization weights. Cool. So this is the key one. This evidence we've already seen in a lot of other papers, which I discussed in the background. This evidence has not been found anywhere yet. And that's what is the big testing point of their theory. So how do they go about testing it? So they employ this one-shot pruning procedure. It's extremely straightforward. Basically, you randomly initialize a neural network, F, that takes some input X and has some initial parameters theta naught, where theta is approximately, whatever that is, I don't know what that's supposed to be. You have some initial parameters of a network. You train the network for J iterations and you arrive at some parameters theta J. You prune P% of the parameters within theta J, and that creates a mask. These are the things that we're going to prune out. And they decide these by removing the smallest magnitude weights, except for the output. The output is pruned at half the percentage of the rest of the network. And then we reset the remaining parameters to their original values, theta naught, creating our winning ticket, where we're masking out all of the parameters that we said we're going to ignore. Right, extremely straightforward. Basically, you just train it, mask out all the lowest magnitude weights, and then reinitialize. Super straightforward. Cool. They also propose an iterative pruning procedure, which works better. It's still pretty straightforward. It gives them better results. Basically, you still just do your random initialization, and then at every, you train for your J iterations, and then you prune P to the 1/n% of the weights, and then you reinitialize, and then you do this again. So for some number of iterations, so say you do it 15 times, you train the network, prune a little bit, train the network, prune a little bit more, train the network, prune a little bit more, and you just keep doing this until you reach your P% at the end. They found that this iterative pruning tends to work better. Cool. So brings us into the experiments and results. So before I get into this, I want to stop and see if anyone has any questions, if anyone's unsure about anything or disagrees with the hypothesis.
So the final step was to reset the parameters to their initial values?
Yes.
And that's the final network that you're using to test?
Yeah. And the argument with that, right, is that other than the parameters that we're masking out, those initial parameters that were successful are winning ticket. Does that make sense?
I think you said, like, is that the network that you're testing with? And it's not, you have to train it again.
Yeah.
No, it'll still be trained in isolation, right?
Okay.
Question, so that it can be reported.
Oh, repeat the questions. Yeah. So the question is, do you retrain the network with those initialized parameters and the rest of the parameters masked out? And the answer is yes. Yeah. Right. Because that's the test. That's the test of number 2. Is when we train in isolation with the key initialized weights, can that achieve the same results as the deep network? Yes?
So the winning ticket actually entirely depends on the random initialization at the beginning of the training?
That's their argument, yeah.
So that means with different random initializations, we can have different winning tickets, right?
Yes,
so,
and there could potentially be many different winning lottery tickets.
Okay, so they, what they showed that for particular random initializations, we have different winning tickets, but they did not actually compare. What if the winning tickets that are found for different random initializations?
Okay.
What
experiments actually? He's gonna show some experiments in different initialization after those mask.
Sure. Anyone else just about the theory, the setup part? Everyone's kind of understands what we're trying to test at least?
Yeah.
Yes.
So the initialization, they do it for glow rod, right?
Yes.
When they say random initialization, is it still from the same distribution
Yes.
glow rod uses, or it's just like another distribution entirely, because they have 2 sets of experiments, right? One with the initial weights and one with random initialization, which they said did not work.
So experiment-related questions asked later.
All of the initializations are from the glow rod initialization, whatever you'd like to call it, distribution or whatever like that. Cool. Okay. So experiments and results, we're going to cover two sets of experiments here, using MNIST, using LINET, and CIFAR 10 using VGG and its variants. So these are the architectures tested. Here's LINET, which is just 3 fully connected layers, 5 technically if you count the input and output. These are VGG's variants, so COMP2, COMP4, and COMP6. VGG's notorious for being extremely over-parameterized. And I believe these came out in 2016. These are variants of VGG, which are much more efficient with their parameter usage. A lot of papers get complained about when they use VGG, and they're like, the reviewers will say, oh, everyone knows VGG is highly over-parameterized. Like, that's a terrible, don't use that. You can't really prove anything using that network. So these are much more efficient implementations of VGG. And then later, we're going to look at ResNet 18 and VGG 19. But ignore those just for now. We're going to focus on these first 2 sections. This one using MNIST, and these guys using CIFAR. CIFAR, excuse me, CIFAR. Someone from CIFAR corrected me about that because they see far. Experiments on MNIST using LINET. So the real initialized networks train slower and converge to a lower accuracy, which this is the test of the first hypothesis. So you can see here, this is the percentage of weights remaining, 100% on the left, 0.2% on the right. And our y-axis here is how long it took for the network to converge. And this one is also how long it took to converge, sorry. And then here is the accuracy. So these guys are accuracy plots. So we want it to be towards the top right, which is more weights removed, higher accuracy. These ones we want it to be towards the bottom right, which is more weights removed, stopped earlier. Okay. So these ones towards the bottom right, we're able to converge much faster. And these ones towards the top right, we're able to converge to a higher accuracy. And as you can see, the solid lines are beating the dashed lines in every case. So here you have solid green, dash green, solid orange, dash orange, solid blue, dash blue. Same over here, solid red and dashed red. So sorry for the people online. I should probably be doing this over here. But yeah, you can see, right? Cool. So the solid and the dashed up top. I'll use the laser pointer from now on. Okay, so test 1 is passed. Test 2 is training pruned initializations. So these pruned networks with this original initialization, they can converge to the same or even higher accuracy within the same number of iterations trained. So this tells us there's nothing interesting or unique about having a very deep, wide network other than it found this initialization that trains very, very well. So test 2 is passed. So I'll walk through this. It's the same thing. Here's training iterations on the x-axis, and the y-axis on all of these is test accuracy. So on these, you want to be towards the top left, which is converging faster and to a higher accuracy. Our blue curve is the standard deep network. That's 100% of the weights. So this is kind of our baseline, is this solid blue. Okay. 51% of the weights removed, or 51% of the weights remaining and 20% of the weights remaining actually both perform better than the deep network. And then over here you can see that they removed the orange, but the red, which is 7% of the weights remaining, performs better. And once you get down to about 3.6% of the weights remaining, so almost 97% of the parameters removed, we finally fall back down to that original accuracy. And then if you keep removing weights, we're now up to about 98% of the weights removed. It finally starts to hurt the accuracy. So this brown here would technically not be a winning ticket because the accuracy is lower than the original network. And then on the right are the experiments with the reinitialization. So we take these exact same architectures, but instead of copying over that initialization, we reinitialize all the weights, just like we did when we initialized the deep network. We're using the same distributions, the same everything. It's just a random initialization. And you can see that the what colors are these here? Magenta and cyan curves are both lower than the dark blue. So you can see the cyan, the magenta, and then the dark blue. Cool. So kind of talk about some of the patterns that emerged. So a winning ticket comprising 51% of the weight to the original network reaches a higher test accuracy faster. Although it reaches a higher test accuracy slower than when only 20% of the weights remain. At 20%, early stopping occurs 38% sooner. With further pruning, learning slows. So basically the pattern is here, when you're removing weights, it converges faster, which makes sense. There's less weights to optimize. But that only works to a certain point, about 80% of the parameters removed. After that point, learning becomes harder again. So you get this hill of how long it takes to converge. They don't dive into that too much. They do cite another paper that refers to Occam's Hill, which I guess relates to that. Test accuracies increase with pruning, improving more than 0.3 percentage points when we only have about 87% of the parameters left. After this point, the accuracy starts to go down, and we reach the original level at about 3.6%, and then they keep going down further than that. So you saw that in the plots. So what is the takeaway? The takeaway is that networks learn faster and reach higher test accuracies the more they are pruned, until somewhere around 90-ish% of the parameters are removed. After that, and in their case, after about 87%, the accuracy really starts to get hurt. And you notice this in a lot of the pruning papers. They all kind of arrive at this 90% number roughly. As you look at the literature, everyone says about 90% of the parameters are useless. This is usually the argument that or the way that they phrase it. Here's some more results. This is early stopping on the left and percentage of weights remain on the right. So here we want to be towards the bottom part of the curve over here. These guys are accuracy, so we want to be towards the top right. And as you can see, both for the one shot and for the iterative pruning, there we go. So these are the one shots. So we want on this curve, green to be lower than red, and over here, green to be higher than red. And then same with the blue and the orange. We want blue to be higher than orange, and we want blue to be lower than orange. Pretty straightforward, cool. And basically all these are showing is that their iterative process works better than the one shot. Accuracy at the end of training, self-explanatory. Okay, and then this guy is just showing the early stopping iterations for one shot pruning. And again, bottom right and top right. So you can see the trend here. The thing that was interesting about this one is that nothing. No, this is exactly how we expect. Okay, cool. So they also did those variants of VGG, right? The COM2 variant, the COM4 variant, and the COM6 variant. And here, basically, all the solid lines are their method. All of the dotted lines are just randomly reinitializing. So on the top left over here, we want the solid lines to be lower, which they all are. Over here, we want the solid lines to be higher, which they all are. Same thing over here and over here. These are all accuracy plots. This is at different amounts of training, so at 20K, 25K, and 30K. So they even show at different points of training that their method works a lot better. And obviously with more training, you get better results. Cool. Fun stuff. Some patterns. This is not very interesting. It's basically the same as we saw. It trains faster, the test accuracy improves, and all three networks remain above the original test accuracy. So super cool. They do mention a brief note on dropout. I mentioned this kind of earlier. So dropout actually increases the initial test accuracy, 2.1, 3%, and 2.4% on our variants. The iterative pruning increases it even further. They give a possible explanation of this, and it's actually one I really like. And they argue, so it's known that dropout increases sparse activations. That's from this 2014 paper. And so they argue that it's possible that dropout-induced sparsity primes the network for pruning, aka it makes winning tickets easier to find. And what that means is if dropout is kind of forcing sparse activations, and their method is throw away the ones that are close to zero, it makes it really easy to figure out which ones to throw away if dropout is forcing a bunch of weights to zero. Right? So dropout's already making it really easy for them to decide which ones to get rid of because it's forcing sparsity. So that's actually a really nice explanation of why dropout helps. So the results with dropout, basically nothing really different here. Oh, this was the curve that was interesting. So here again are solid lines. This is how long it takes to converge, and this is the percentage of the weights remaining. And you can see with dropout, it actually takes longer to converge. That was kind of an interesting result, but the accuracies here are far better. So the solid lines are above all the dotted lines over here, but it takes longer to converge. And the reason for that is something we talked about on Monday, and I can't remember what it is right now. I'll come back to that. There's an interesting reason Dr. Bagci and I figured out of why that's occurring. So that brings us to their final set of experiments, and one that they got a lot of criticism for is deeper networks fail. Deeper networks don't perform the same way that these shallower networks are, like LaNet and the VGG variants, the small VGG variants. So VGG 19, which is huge, and ResNet 18, both on SciFar 10, they moved to a global pruning because the layer-wise pruning wasn't working. The global pruning worked better, but it still didn't help a ton. Basically, all this means is that instead of removing P percentage from each layer, they remove P percentage just anywhere, wherever the lowest weights are. At a higher learning rate, the iterative pruning doesn't find any winning tickets. When they lower the learning rate, they get their usual pattern to reemerge, but only very, very early in training. And then the original deep network, takes off, and they can't ever beat that deep network accuracy again. They started to use some tricks like learning rate warm-up. I think everyone's familiar with that. We basically started at a lower learning rate, crank the learning rate up, and then taper it back off again. Using that, they were able to find some winning tickets with VGG, but even that didn't help with ResNet. This is an interesting thing. So if anyone read the comments on Open Review, the authors of SNP kind of came at them and said, in our paper, we show that you can prune 80% of the weights, reinitialize, and still meet the test accuracy, which seems to contradict them. That says if you reinitialize, the accuracy is lower. But they show that, yes, up to 80%, this is true. You can reinitialize. And that's because these networks, and they use VGG 19, these networks are so highly over-parameterized that even at 80% of the weights removed, there's still enough tickets to find a winning one. But when you start pushing it up to things like 98.5% of the parameters removed, there's just not enough of those random subnetworks to find winning tickets anymore. And the accuracy quickly falls off when you reinitialize, but the accuracy stays high when you take that special initialization. So they show that their theory does hold if you push past that 80% mark. So here's the results for VGG 19. These plots aren't very interesting. They're just pretty noisy, and they just show that their method's failing. And I'm already tight on time, so I'm just going to kind of flip through these. So yeah, nothing really special here. So strengths and weaknesses of the paper. Yeah, so this presents a theoretical insight into why these deep, highly over-parameterized networks perform better than their shallow counterparts. Because everything in our current theory says that they shouldn't, right? Pruning, the universal approximation theorem, right? There's all these things out there that say that shallow networks should do just as well. So why the heck are these deep networks performing so much better? And this paper provides a nice theoretical insight that brings these two together, that says, no, shallow networks can perform just as well, but here's why the deep networks are performing better. And it's the key is this combination of a special initialization with the way we optimize during training. It ties together many important theories, right? So it brings in dropout, it brings in optimization, it brings in generalization, bounds, and this idea of Occam's Hill. And it brings in this paper that was also at ICLR 2019, which is optimization to a global minima. It was a paper at ICLR 2019, and it's cited in the work if you want to find it, that says a 2-layer ReLU with a quadratic loss does converge to a global minima under SGD. So if anyone's curious about that, you can go read it. It's in the paper. But it brings together a bunch of things in our field right now. So this is kind of a nice theory that kind of ties everything together. It also provides a large number of empirical and theoretical evidences to support their hypothesis. I didn't really find anything I could challenge them on. But we'll open that up to questions. Weaknesses, they only present results on CIFAR 10 and MNIST, not something like ImageNet. And this is like the laziest, easy criticism to give to a paper, right? Like, oh, you're just using toy data sets. Unless you do ImageNet, I'm going to reject your work. And it's very frustrating because a lot of us don't have the GPUs to train on ImageNet for 2.5 weeks and, you know, converge a nice model. That being said, their entire premise is that on large-scale tasks, deeper is better. So if you're only using toy tasks, it's kind of hard to make the argument about, you know, deep networks being better, right? I don't know if a very large diverse data set like ImageNet, if they're going to see the same patterns. And they're already not seeing the same patterns with big deep networks, but they're using big deep networks on toy data sets. So it becomes kind of hard to hold their evidence up to scrutiny when you're only using toy tasks. The performance on deeper networks is very disappointing. This is the obvious one. They require these, you know, kind of hyperparameter tricks, and sometimes they still fail even with every trick they can think of. They actually solved this in their follow-up paper. If anyone saw this, stabilizing the lottery ticket hypothesis. And I'll talk about it briefly. I don't have time to obviously go through the whole paper, considering I have 30 minutes and this first one was 42 pages. So. But just a brief note, they come up with this new technique called iterative magnitude pruning with rewinding. It's the big thing. So instead of looking at the neurons at initialization, which is, you know, rewinding back to theta 0, they instead look at the weights after several training iterations. So they'll train it a little bit and rewind to that point instead of rewinding all the way to the beginning. And their argument is that some neurons, you have a winning ticket rated initialization that's just really lucky. Some of them need to move to their winning position after some amount of training. Kind of makes it a less exciting theory, but it's still pretty cool. So they kind of notice this pattern of neurons whose values don't change are typically part of the winning ticket. So what'll happen is neurons will move a little bit at the beginning and then sit there, and they won't update anymore after that. Versus other neurons, their values will keep changing. There's a lot of noise in them. Those are typically the ones that are gotten rid of. And they do it on actually big networks now, ResNet 50, SqueezeNet, Inception V3, and they're able to find winning tickets very early in training, 0.1% into training, up to like 7% into training, that are 50 to 99% smaller while achieving equivalent accuracy. So from an empirical point of view, this is very exciting. From a theoretical point of view, this first paper is more exciting, but the little caveat makes it work for, you know, bigger, deeper networks. Cool. That's everything. I'm right at 30 minutes, so I guess questions or anything like that.
We can start some discussion.
Okay.
So you will guide, and some of them you can repeat the questions so that they can hear us.
Okay.
And okay, let's get some questions.
Easier to remove in fully connected layer 1 weight, but how they remove the weights in kernels? The convolution is 3 by 3.
Right. So the question was, in a fully connected layer, it makes sense to just pluck a single weight out, but how would you do that in a convolutional layer where you have a kernel? I'm assuming, this is partially my assumption, I'm assuming they drop whole neurons. So they would drop a whole kernel. And they do that with the lowest magnitude, I guess, of the whole kernel. That's an interesting question. They don't really mention it. They don't really mention, they basically say that the way we drop is not important. You use any pruning procedure you want, we don't care. Just whatever you get to that's pruned, that's your winning ticket. I don't care how you got there per se. So they don't really focus on that in the paper, but I'm assuming they use whole neurons.
I think the layer-wise pruning was not, they were not really proposing that, right? They were saying it is not optimal. So they do global pruning, which means they just rank all the neurons and they select those things without having them. In layer-wise, probably they remove all of them, like the kernel. But the other way, you just rank all of them without having particular order.
Even in that, let's say, if one weight of that filter, if that comes to
it should be died off.
So what does that, how does that make sense?
I assume it's they kill all.
Yeah, I assume they kill a whole neuron. I mean, you could, in theory, kill just that weight, set just that weight to, mask just that weight out. And then it would just be the sum of the rest of them, I guess, right? I mean, in theory, you can do that, but I'm assuming they just drop the whole neuron. That would be a huge pain to program that. Cool. Any other questions? Yes.
Several confusion about the hypothesis. Is this about finding the sparse network and the correct initialization, or is it just about finding the correct initialization? Because let's say I have a network and I want to train it for some ABC task. Now, I am supposing this network is the sparser network for some other deeper tensor network. So now for this network, if I have the correct initialization, not just random initialization, the correct initialization of the original network, it will perform a lot better than with some random initialization. So I think it's just about finding the correct initialization for any network.
Yeah, so let me see if I can summarize your question efficiently for the viewers. So basically, the question is related to, do they care specifically about the pruning method, or are they more interested in just finding this random initialization? And your argument is that all they really care about is the initialization, right? Is that kind of what your question says, right? So yeah, and they specifically mention in the paper, and especially in the reviews online with the snip who comes at them and says, hey, our pruning method gets X. And they said, yeah, go ahead, we'll plug your pruning method in. We don't really care what the pruning method is. All we care about is whatever the prune down network you arrive at, grab the initial weights from those. So a big criticism that you see from this, which is frustrating, is they say, well, there's no immediate value to this work. And what I mean by that is how do we take this and use this there's no application. That's the right way. There's no immediate application of this, which is frustrating because it's a beautiful theoretical work. But there's no immediate application because I still need to take a deep network, train it completely. And in fact, if I'm doing the iterative pruning, I need to train it completely 15 times. Or however many n is, right? And then once I have the prune network, then I can retrain the prune network on my task. And it's this sounds like a very inefficient way of doing deep learning. And that's a legitimate argument. They're not claiming to be an application paper. So there's not really a good use for this. It just provides insight. Does that kind of make sense? So yeah, go ahead.
Yeah, I completely. I just want to say the same thing as you and asking the same thing. Do you agree that these those insights into the weaknesses of STD and kind of doesn't give any way to fix it, but says a remedy that after it is done, we can fix it. You know, I was wondering because I read the same paper in CDPR about neural rejuvenation, that they witnessed the same thing and said that, well, why not do this during training? When it's training, we just, if we see that the sub network is becoming dominant, we kill it. We let the rest of the network become powerful, and then we let the sub network again train. And then if another network becomes dominant, we kill it during training. We don't take this decision and let another part. This way, the whole network becomes more powerful. I think this paper gives a great insight in SGD, but doesn't give a way to solve it. And I think neural rejuvenation does that.
Yeah. So this is an interesting question. I have sort of two parts back to it, and I'll try to summarize in my response what exactly he's saying. The first part we can talk about is the neural rejuvenation. If anyone hasn't seen that paper at CVPR this last year, neural rejuvenation, blah, 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 subtitle, it's a very interesting paper. They basically show that when you train a big, deep neural network, a lot of weights go to zero. And during these sparsification algorithms, you can basically get rid of 90% of them. They say, well, what if we don't let that happen? What if during training, anything that starts getting close to zero and becoming dead, reinitialize it randomly? So do the same random reinitialization. Now, don't copy and paste over whatever the random initialization happened to be at the first time, but just reinitialize it randomly. So every time you notice part of the network dying, reinitialize that part of the network. And they keep doing this over and over, and they show that doing this and not allowing parts of the network to die, not allowing a network to become sparse, gives you better results across a variety of tasks. I have not been able to reconcile that with this work. Because I don't quite know how. Their argument is that there's nothing unique about a deep structure, that it's a random subnetwork within there that's important. But neural rejuvenation, they show that the combination of a huge network all contributing is better than what these guys would take, right? They'll take their sparse network out and say, yeah, we can achieve just as high of accuracy with a super sparse network. And neural rejuvenation says, that's great, but if you force all of it to work, then you get even better results. Yeah, I don't really know how to reconcile these two concepts yet. I've actually been thinking about this.
I have an idea about that. So why not think of it as neural rejuvenation kind of forces many subnetworks to be optimized?
It does.
And SGD just sticks to the dominant one and tries to make that the most optimized one. But neural rejuvenation also masks out the dominant one. I think if you focus on that part, it doesn't allow the dominant one to be optimized. It allows other subnetworks to look at the problem from different angles. I want to put it that way.
Yeah.
And
yeah. We agree on the premise of how it works. What I'm concerned about is a bigger lottery ticket better than a smaller lottery ticket? Right, in the context of this, if I take a standard training procedure and just take the special weights, that gives me the same accuracy or even better accuracy. But they're showing that if you force the whole network, which is a bigger lottery ticket, you get better results. And it doesn't directly contradict this work, but it throws an interesting wrench in there, right? Which says, you know, maybe there is something better about a deep structure other than just finding a random subnetwork. Maybe multiple subnetworks, you know, coordinating is better than a single subnetwork. And that might be the case. I mean, that's definitely the case in neural rejuvenation if that's your only evidence. Yeah, I guess multiple lottery tickets is better than one. To your point about SGD, anyone who hasn't thought about this, it's very obvious from the universal approximation theorem that SGD sucks. I mean, it works. It does what we want it to do, but our optimization techniques are terrible because non-convex optimization is hard. If anyone didn't know that. So yeah, I mean, very clearly we should be able to take a single layer network and train it to approximate anything. That's what the universal approximation theorem says. We know that it's right. It's mathematically proven, but we can't find those parameters. Finding those parameters is very hard, and that's optimization, is finding the parameters. Our techniques of optimization are not great. We've been using SGD forever. There was another one proposed last year or 2 years ago that was Hamiltonian descent, which basically is the second derivative instead of the first. Had some interesting stuff there. There's not a ton of people working on brand new optimization techniques. It's mostly Atom plus X or SGD plus Y or, you know, so.
Controversial findings there. Huh? We discussed some of them, like yellowfin and.
Yeah. There's a lot of yellowfin's an interesting paper. P-Atom is an interesting paper, a probabilistic implementation of Atom. There's a lot of interesting papers, but fundamentally, if you rely on SGD, which all of them do, it's a suboptimal solution. And I don't know if there is an optimal solution to a non-convex optimization problem, right? So
and here, I think so if you choose Atom or SGD or whatever, I think the main idea is, so you need to be close to the solution wherever you start. So some of the optimization methods may be better than others. The idea is, you know, it can take maybe lower number of iterations, but you need to be close to the solution. So I think the main issue is not really the SGD. SGD has its own problems, I agree. But you know, what they say is really, you know, the math, and it exists in other fields as well. So we were discussing for segmentation, right? So if you are in the close vicinity of object, you segment better. So if you are in the close vicinity of the true solution, you are better. And for the same thing, like for the same the problem, you can demonstrate in multiple different ways. So there's this mathematical paper that says local minima of deep learning is global. So you have so many, and some of those local minima are actually global.
That's super controversial right now.
Yeah,
that's super controversial.
I know.
Because some travel papers, just ICLR just came out this year that says this kind of network does converge to the global minimum, but then other papers say no. If you converge to the global minimum, you're actually going to overfit and it'll be bad. And then other papers say no, it is the global. That's super controversial.
It's like also this optimization things, right? There are, you know, papers say the opposite because they, you know, they are all based on experimental findings. You know, they find some evidence. Okay, great.
So you had a question.
Yeah, so I would continue this thing. They have mentioned it in the paper on page 8, the importance of training integrated initialization. And this is the title of their paragraph. So they say that the benefit of initialization is connected to the optimization algorithm, data set, and what. So it is not about SGD or
yeah. And many things, like, you know, yes, they say initialization is very important, but one of the paragraphs is that architecture is also, but it's more important, they say, than initialization, because it matters now, right? Because based on evidence.
Yeah, so it suggests that if you have SGD and you have the initialization, the optimized initialization, and if you take that optimized initialization and you change your optimizer to Atom, then it would not.
Yeah, you change anything. Yeah, that special initialization is only for that network, that problem, that optimizer, that everything.
But so how is it? They are claiming that it gives us generalization. But they are also saying that it is connected to data set.
How does it connect to generalization? There's a paragraph towards the end where they kind of talk about that. And they say, let me pull it up here. Make it easier. I don't want to paraphrase them terribly, so give me half a second to actually pull up the paper for you guys. You guys use Mendeley? It's pretty nice. So they talk about generalization here towards the end of the network. Points of
On page 9.
Is it on page 9 here?
Improve generalization.
The last one.
Well, there it is. Yeah. Yeah. So their argument, and it's based on some actually interesting evidence, is that right here. So there's a relationship between compression and generalization. And the argument is that these compressed networks, these pruned networks, are guaranteed to generalize better than deep networks. And they don't really dive into that. They basically just cite some works and say that this is kind of a known thing. And they cite this like 1986 work, plus some other recent ones, right? So tighter generalization bounds that can be compressed further for pruning and quantization. Also noise robustness. So you'll have to kind of go either take their word for it and go look at these works, or just go look at those works and see how exactly they relate. But it is sort of known, or at least accepted right now, that these pruned networks, these quantized networks, these compressed networks do generalize better, and they are more robust to like noise. And that has to do with them not being highly over-parameterized.
For this particular paper, they based on based on the test dependent, and it is higher than the others. So that's why they say, because generalization is tied to test. Something we didn't see before, and now it gives you better result. They claim that organic is generalized better, and give other papers, which has actually a nice theory about how compressed networks and can generalize better.
Yeah, and some small empirical evidence exactly from the paper that while the training accuracy they achieve with the small networks is basically the same, the test accuracy is higher. Right, so even though they're achieving the same training accuracy, they're achieving higher testing accuracy, which is generalization. So, yeah.
The smaller sets that they didn't have any, or the smaller networks they didn't have any problems with initially, like excluding the BGG and the ResNet.
Mm-hmm.
Did they ever mention it on the extra supplementary pages that there was a time where they initialized randomly and did not find a ticket? Because they don't really say anywhere about, like, they don't prove existence. They just show empirically that usually from our tests we find one.
Yeah, no, and they do kind of make a little note about that we can't guarantee that the winning ticket is there. Only that the more tickets you buy, the more likely it is that one is there. No, I don't think I don't believe they discuss anywhere about failures in that case.
Yeah.
I think as a one there, it could be that your initialization is not good enough to have any winning ticket for that initialization, right? So it could happen that you have random initialization. They say that initialization is an important key there, right? There could be one initialization which is random where you can have no winning. Right.
You could also say the initialization methods. One method might be better at finding winning tickets than others.
You could have an interesting if they have shown different, they work with different initialization techniques like
and show that ones are likely to find better tickets.
But I kind of disagree that there cannot be any winning ticket because SGD never fails in training a neural network, at least a deep neural network. Again, you always will have some answer. That's the whole point of optimization. And just the winning ticket is there. I think this is also a good question because it tells us why they're failing a deep neural network. There's more parameters, more randomness, harder to find a better solution. So they wait a little bit so that the solution arises itself. I'll say that there is something in there that SGD will find in the end. It's just not something that you see as a thing. But SGD will find a way. SGD will converge.
Well, SGD will converge to something.
Yeah, some.
But so we got to be careful with our definitions a little bit because the winning ticket is defined based on the accuracy of the full-size network, not based on some external what we expect the accuracy to be, right? So if it performs terribly and we get our winning ticket which performs just as terribly, but as good, that's a winning ticket. That has nothing to do with how good or bad the network is doing on a particular data set. So not being able to find a winning ticket is an internal question, right? It's not whether or not the initialization gives us really good results. So there's something deeper there. That's, yeah.
Let's say we have two initializations and a single network. And if we train the network with both these initializations separately, and we clone the network, should us be getting same structures or different structures?
So they
should prove it wrong. I mean, they should prove that both are different.
Well, they do say that the structures they find do tend to be similar in nature, which you kind of expect because the architecture isn't meaningless, right? For example, like if you're designing a neural net, you wouldn't put one filter, one layer, one filter, one layer, one filter, one layer, 1,000 filters, and then one filter and expect it to perform really well or something, right? Like the structure isn't completely irrelevant. So you would expect for a given task and optimizer that some structures will perform better for that set of data. So you would expect some sort of pattern to emerge, but it's not going to necessarily be identical.
For every random initialization, we will be getting same accuracy.
Not the exact same architecture necessarily, but you would expect it to converge to a similar structure. That doesn't disprove their hypothesis in any way.
For a single data set.
For a given data set, yeah. And they say that this work can help provide insights to what are the optimal structures for a given problem. And you do, right? You expect the network to kind of converge to something similar. And you see that in a lot of papers. There's a ton of papers out in the last year and a half of randomly connected networks and efficient net. And what are some of the other papers? There's a ton of them out right now. Efficient net got the most publicity of basically taking randomly connected networks and then seeing what randomly removing connections and adding connections and seeing what it kind of converges to, and patterns emerge. So there is an optimal, we believe that there is an optimal structure for a given task. We don't believe it's just random.
So if I remember correctly, in appendix, they have a section where they say the fan in and fan out tendency for the prune network. So it does follow some pattern. So they can't actually like give the entire structure, right? But they say that there are some neurons which will be more important to give outputs, fan in and fan out. That's it.
Yeah. Do we have? Yeah, go ahead.
Yeah, so more of a clarification. Actually. There's one line that mentions which said improvements suggest iterative pruning interacts with dropout in a complementary way. So dropouts would technically be random one-shot pruning.